What is a random variable? Well, we've been dealing with randomness. We've been dealing with chance processes, okay? We call something a random variable when we attach a numerical value to a chance process. So that's like a key idea, is that random variables are in fact numerical in nature. All right, so I want you guys to imagine, and we have two types of random variables, okay? We have discrete random variables and we have continuous random variables. Now, we have quantitative variables in statistics and we have categorical variables. And then within quantitative, we've already kind of talked about discrete versus continuous. And an example of a discrete variable is shoe size. An example of a continuous variable is foot length. Both very related to each other, right? Your shoe size is based off of your foot length. Okay? So, why is shoe size discrete? Does anybody out there wear a 7.234 shoe? You either wear a 7 or a 7.5 or a 7.5. So discrete variables kind of have this like fixed level of precision, whereas continuous variables, I can get more precise as long as my measuring tool can get more precise. Like your foot length could in fact be 6.3475432 inches long, depending on how precise we want to get. Everybody good? Though, I don't know. All right, now let's take a very classic chance event, coin flip, but this time instead of flipping one coin, we're going to flip 3 coins. Everybody good? All right, what are the possible outcomes? Okay, so for the first coin, we can map that out as heads or tails. And then we flip, the second coin. Then we flip the third coin. And if we wanted to, I could kind of trace each branch here. And if I trace this first branch, I have heads, heads, and heads. So that outcome is heads, heads, and heads. Everybody good? And then I do the next branch, and it would be heads. Oh, boy. I thought that was a highlighter, y'all. Heads, heads, tails. Do you guys see what's going on now? Okay, as we list our possible outcomes. So we have heads, heads, tails. And then we would have heads, tails, heads. And then heads, tails, tails. And all I'm doing is tracing the different branches. How are we feeling so far? Now, looking at these 8 outcomes, which one is the most likely?
All of them.
All of them are the most and least likely, right? They all have the same probability. Because, each branch is 50-50, and then all of them would be like 0.5 times 0.5 times 0.5, and then 0.5 times 0.5, and I'm going to shut up now. Okay. All right. Now, we just said Random variables take on a numerical value. Do any of these have a numerical value right now? Like looking at these. No. Could we create one to summarize these? Yeah. What do you want to call it? You know what? I'm going to call this one, let's call this 3, 2, yeah, I know. 2, 2, 1, 2, 1, 1, and 0. Can anybody tell me what my numerical outcome for each, my numerical value for each outcome was? The number of heads. So we can take a categorical variable like a coin flipping heads or tails, and we can turn it into give it a numerical value by just counting my number of a version of successes. Okay, so number of heads. And guys, for number of heads, is this a discrete or a continuous variable?
Discrete.
This is discrete because on any one set of flips, right? Ain't no way I'm going to get 1.25 heads. It isn't happening. How are we feeling so far? All right. So now, wow. So now our probability variable x is going to equal that number of heads, and what are our possible outcomes? Well, we either got 0, 1, 2, or 3. And if I asked you guys, what's the probability that none of the coins come up heads, you would say 1/8. And if you guys don't mind, I'm going to write that as 0.125 just because I like to keep everything nice. And are we comfortable with that idea? What's the probability I get 1 heads? Well, that happened 1, 2, 3 of the 8 times. What about 2 heads?
3/8.
Another 3/8, so I'm just going to write this 0.375. And then 3 heads was...
1.
Whoa. Now, we started talking about probability distributions. And a complete probability distribution has every possible outcome. And the way we know we have every possible outcome is that the probabilities would add up to 1. So looking at this, is this a complete probability distribution? Sure is. Sure is. All right. Now, way back, we've drawn histograms before. Okay. Does anybody remember what the label on the y-axis was for a histogram? It was either frequency or relative frequency, but given that we have probabilities here, I'm going to call it relative frequency. Because essentially, isn't that what a probability is? How often something should occur in a large number of trials. Okay, so relative frequency on the y-axis.
Thank you.
I've learned over the years. There's a certain look in your eye.
A certain.
Yeah. Can I zoom out? Guys, this is a beautiful histogram. Don't you guys love this? Yeah. We didn't just draw histograms before. We used to have to describe histograms. Can anybody remember the 3 things I would ask you to describe when describing any graph of a distribution, in particular a histogram? Shape, center, and spread. All right. Without using the word normal, because I have reasons for not wanting to call this normal. Basically, I don't want to call this normal. Because while it looks bell-shaped, with discrete variables, especially with only a few possible outcomes, it's really uncomfortable for stats people to call a discrete variable normal. Can you guys trust me on that? Mm-hmm. Okay. So without saying normal, how might you describe this shape? Mound-shaped. Mound-shaped? There's another really key idea that I would put into this. Not just is it mound-shaped, symmetric. Are you guys comfortable with mound-shaped and symmetric? If you wanted to call it unimodal and symmetric, that would be great. Okay. What about the center? If you had to estimate the mean of this histogram, what would you say?
That's the median.
And the mean.
Oh, it's the mean too?
The mean and the median are going to be about the same if the distribution's symmetric.
Oh, okay.
In this case, they're identical, but yeah. Okay, now, you guys, the mean is not talking about one trial. It's talking about lots and lots and lots of trials. So it's okay that the mean is 1.5, even though it's impossible to get 1.5 heads on a trial. Okay, all right. Now, what about the spread? Before we used range, we talked about the IQR. There was one other measure of spread. Does anybody remember what the last measure of spread is? Not what is it for this particular graph. Fairly important one. Standard deviation. Okay. This graph has a standard deviation. I don't know what it is. I should probably just figure it out real quick. I'm going to call it 0.72. I don't know what it is exactly, but it's probably pretty close to that.
Is there a reason you're not using range or range?
Because eventually I'm going to ask you to find the mean and the standard deviation of probability distributions instead of using the range.
Okay.
Eventually. We may or may not get through that today. It really just depends. All right. Now, as you guys know, Thanksgiving is coming up, and Miss Meister can't afford turkey. So we're going to play a little game to try to help Miss Meister earn some extra cash. You guys cool with playing a game? Turkey's expensive. Also, Miss Meister's least favorite food.
Turkey?
It's so gross. It's dry. I hate it. All right, so here we go. This game is just gonna involve a very simple 4-section spinner that has 2 blue sections. We'll put them here and here. A white section and a gray section. All right, so if I spin this spinner right now, what is the probability it lands on white? And if it lands on gray, 0.25. If it lands on blue, 0.5. So are we cool with saying in this case, this is no longer a 50-50 situation-ish, okay? And here's how the game's going to work. All right. Each of you is going to pay me $1 to spin the spinner. Is everybody with me? And if it lands on white, not only am I going to give you your $1 back, I'm going to give you another $1 as well. Is everybody with me? All right. If that's the case, what is your gain? You're walking away $1 richer, yes? So your gain would be +1. Did we just take that categorical variable of landing on white and assign a numerical value to it? Is this okay? All right. Now, what if it lands on gray? If it lands on gray, I'm going to give you $1 back. So you're going to pay me your $1, and you get your $1 back if it lands on gray. What's your gain? All right. Now, if it lands on blue, sorry about your luck, I get to keep your $1. So your gain would be -1. So we've just assigned those numerical values. So now what is the probability your gain is $1? Well, it's equivalent to the probability that you land on white. So you're going to gain $1 25% of the time. What do you guys think of this game?
Doesn't look too good.
It doesn't look too good? Why? You're only going to lose money half the time. It's a 50-50 shot whether or not you lose money. Right?
Yeah, but there's only a 25% chance you gain money.
Could we have rewritten this from Miss Meister's perspective? What's Miss Meister's gain if you guys land on white? -1. 0, +1, yeah? And now we could look at this and say, oh, Miss Meister's only making money half the time. Okay. Are these discrete? Yeah. How do I know they're discrete? You can't win $1.20 or can't win 75 cents, right? You either win a 0, 1, or -1, right? Okay. Are they both legitimate probability distributions? They're two separate ones. I'm going to go with yeah. Now, how do I know that? All those probabilities add to 1. It's every possible outcome. Would you play? What do you think? Would you play this game?
Yeah. Worst comes to worst, you lose $1, but then you could get another $1. What?
I love it. Let's all play. Because what's going to happen in the long run, y'all?
You're gonna make money.
I'm going to make money. Right? Would you play over and over and over again? You know who would do this over and over and over again? In fact, they did this over and over and over again last week. This guy with the lottery. But the pot was big enough that I felt like it was worth spending $2 for a lottery ticket, right? Did you guys know how big it got last week? $2 billion.
Somebody just has, well, after tax, not as much, but somebody just has all that money now. That's crazy.
Well, they sort of have all this money, which is a conversation for a different day when we're bored. But the lottery does a few things there that are that are choices, is what I'm going to say. They make some choices that I find interesting. But it would be nice to win $2 billion, right? Mm-hmm. Guys, just so you know, the first thing I thought about was what I would do with $2 billion. And the answer is rent costumes for the musical. For sure.
Yeah.
For sure. Okay. Just so happened to be the timing, I think. All right. So will I make money? Yes. Why? That's the explaining why is a kind of a tough kind of thing, right? Now, the reason happens, so let's imagine a large number of trials. Like, I don't know, 100. I find 100 kids to play this game with me, right? Right. And so if that's the case, how much am I going to win?
50.
We'd expect to get $50 in winnings. How much am I going to lose? And how many times am I going to tie? 25 times, but the total loss there is 0 because I don't lose anything on a tie. Do you guys kind of see what's going on here now? Okay. All right. And there's several establishments, such as casinos, racetracks, or whatever. It's not that they just stack the odds. What they do is less about only probability and the way they set up how much you win so that, like, for instance, so that it kind of rigs in one way or the other. Do you guys get what I'm saying here? So they make the payouts one that even when you win, you lose in the long run. Okay? How would you change the payout to make this fair? Could we make this fair?
Yeah.
What would you want to do? How much should I pay you if you win to make it fair? $2. If I paid you back $2, all of these 25s become 50. Right? Every 25. Okay, I'm going to shut up now. Okay? All right. So games of chance in general are rigged against the player, and they're rigged against the player for a large number of trials. And so when you go to a casino, right? When Ben turns 18 and he wants to go play blackjack, right? All right? The casino couldn't care less if he wins, as long as there's a lot of people playing. Does that make sense? That's how casinos make their money. Cool? All right. Let's talk about this in the calculation world. All right. So, a probability distribution of a random variable has a mean, which is called the expected value of x. Sometimes we call it the mean, using that mu notation, okay? And the way you find the mean is you take the sum, remember that sigma means sum, of each data value times its probability. This will be given to you on a formula sheet. All right. What we call the variance of x, which, by the way, is the square of the standard deviation. Okay? You calculate by doing the sum. You're going to take each value minus that mean and square it times its probability, which is really fancy formulas. I'm going to take you through them, okay? Then I'll show you the shortcut in the calculator. So the table of your guys' gain on the previous page was that you would win 25% of the time, break even 25% of the time, lose 50% of the time. Okay. So here's what we're going to do. To find that expected value of x, we're going to say, hey, when x was 1, the probability was 0.25. So you can do 1 times 0.25 plus. So you're just going to take each outcome times its probability and add them all together. And you guys, you're going to end up with negative 0.25. And that all this formula is the outcome times its probability, okay? And the mean formula, I think, is a relatively reasonable expectation to have you guys calculate, okay? Then we will find the variance. This is the one that you're going to hate. Relax. But if we don't get to it all the way through it today, we will by tomorrow, okay? All right, so to calculate the standard deviation, you're going to calculate something called the variance first. And to calculate that variance, we're essentially going to do we're adding together. I have 3 different things I'm adding together here. Why? Because there's 3 possible outcomes. Good so far? So what are my 3 possible outcomes? The 1, the 0, and the negative 1. So those are going to go here. That's just the xi of the formula here. Okay. Then we're going to subtract the mean. What was my mean? Yeah. The negative 0.25. The mean that we just calculated. And then we're going to take each one of those times its probability. So the probability of 1 was 0.25. The probability of 0 was 0.25. The probability of negative 1 was 0.5. And then, in theory, we would type this whole thing into our calculator and we would get 0.6875. Duh. And this just told us our variance, which was the square of the standard deviation. So now, the last thing we could do is if I take the square root of that, that'll give me sigma. And for this one, we get 0.829.
So is 0.829 the final answer?
0.829 is the standard deviation. So it technically depends on what I'm asking you for. So if I'm asking you for the mean, the answer is Negative 0.25. If I'm asking you for the variance, it would be the 0.6875. And the relationship between the variance and the standard deviation, that squared square rooty thing that's going on there, that will become quite important towards the end of next week. Okay? Now, you guys, this is a pain in the something. Is everybody with me on that? So I want to show you something in the graphing calculator. Okay. So what I'd like us to do there we go. What I'd like you guys to do, there we go. So this should put the recording of the calculator part in there for people. Okay, go ahead and hit Stat, Edit. And what I want to point out is, if you look, my L1 and my L2 here, in L1, I have all the possible outcomes, and then in L2, I have the probabilities of those outcomes. Is everybody comfortable so far? Now, before, when we used the calculator to get like mean and standard deviation, we ran the one variable stats, okay? If I did that on just L1, guys, what's my mean of L1 going to be? If I asked you guys to find the mean of 1, 0, and -1. It would be 0, right? And what I basically need to do is tell the calculator, well, wait a minute, that -1 happens more frequently. So that's why I put in these the probabilities in L2. Is everybody with me so far? Okay, so once we do that, no. All right. Still recording. Okay, so guys, go ahead and hit Stat, and we're still going to go over to those one variable stats. And you guys notice that before, and for you guys, this frequency list is completely blank. We left it blank when we knew each thing had the exact same frequency, so we didn't need to change it. But now what we want to do is say, hey, all those items in L1 happen as frequently as I put next to them in L2. So when you think about probability as how frequently something will happen, your probabilities are your frequency list. And now if you go down and hit enter,
How did you get the L2?
second 2. If you look above the 2, there's an L2.
Oh, yeah.
That's a great question. Sorry, I didn't anticipate it. Is everybody good? Okay. Do you see? Holy moly, you guys. I found the mean. It's negative 0.25. It's not the exact same thing we got. And likewise, you see where it says sigma x? So your calculator can do it for you. Is this okay? All right. So the question's going to become, I'll stop this so that it doesn't, can I stop this? There we go. All right, so the question is going to become, what do I need to see? Is everybody with me? Like, what work do you need to show? And the answer is, All right, so here we go. Let's just do another example real quick. In this case, what we have is if you go to a certain car dealership, they can either sell 0 cars, 1 cars, 2 cars, 3 cars in a given time frame. Okay? And we can see the different probabilities for each of these, right? So if they sell 3 cars in a day, that's pretty awesome. It's in one of the top 10% of their sales days. All right. So finding the mean and the standard deviation here, we're going to get the answers from the calculator, but you still need to show me some work. Okay? So we're going to do 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1. Yes?
Why aren't we writing the mean as the little like
E of x?
or no, the other one. That's like the little U with the leg.
You mean this curly Q mu?
Oh, that is that.
Yes. And I need some help. I don't know what this answer actually is. I think it's 1.1, if I'm remembering from a long time ago. We didn't get to this one last period, which is why I don't know the answer. .1. Okay. And the work you're going to show me for the standard deviation is going to be 0 minus 1.1, the quantity squared times 0.3, plus 1 minus 1.1 squared times 0.4, plus so I'm still filling into the form. You don't have to write it all out, just 3 terms. And so when we get to groups that are like 5 or 6 possible outcomes, 3 will always be enough. You're just showing me that you're just showing enough to show that it's all of them. And you're not typing this into the calculator in the sense of you're not typing this plus this. You can use those lists and use the one variable stats to get there instead. Okay, so when I put these in, one, two, three. Guys, I got the standard deviation to be 0.94. And I just got it from doing that one variable stats again. Okay, don't kill me, we're not done. I want to make sure we understand how to interpret these. Okay? Now, that 1.1 was the average if the probabilities hold. And what do we know about probabilities? They only hold for a large number of trials. So in this case, each trial is an hour on a randomly selected Friday. Yes? So for a large number of Fridays, the dealership can expect to sell 1.1 cars. Per day. Then something like the number of cars will vary. Cars sold will vary from the mean. By an average of 0.94 cars.